The modern periodic table and the periodic table that you have in front of you for the AP exam actually didn't start like this. In the 1800s, a scientist by the name of Johann Dalbinger arranged a periodic table in triads, groups of 3 elements that he saw had similar properties. So, for example, lithium, sodium, and potassium would be one triad because they have similar properties. And his triad periodic table held true until about 60 years later, when a scientist by the name of John Newlands arranged it in octaves, much like scales on a piano. He saw that there was a repeating pattern every 8 elements or so, and he arranged them in that repeating pattern, thus octaves. In 1870, Dmitri Mendeleev rearranged the periodic table by increasing atomic mass, which is very similar to the periodic table that you have now in front of you. His work was expanded on by a scientist by the name of Moyer, who rearranged just a few elements. Mendeleev's periodic table was so accurate that he was able to predict elements that hadn't been created yet, like much of the lanthanides and actinide series. And in 1913, a scientist by the name of Robert Moseley, who did many things for science, but among his chief accomplishments was he rearranged the periodic table by number of protons, which is the periodic table you now have in front of you. When you get your periodic tables for the AP exam, you might want to do a couple things. First off, you might want to go across the top and number the families, or at least the representative families. So hydrogen's family is 1A, 2A, and I'll pause you and fill it in for myself. And you'll notice that I use Roman numerals. Do you have to use Roman numerals? No. When you're writing on your periodic table, you can do 1, 2, 3, 4, 5, 6, 7, 8. But when you discuss them in a free response, please remember to write 1A or 2A. Otherwise, you have to call this 13, 14, 15, 16, 17, 18. Otherwise, you won't get the full points, because this down here is 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. So please remember that there are Roman numerals when you discuss them in free response questions. Another thing you may want to do is go ahead and put the principal energy level of each row, or just number the rows because it's the principal energy level. And I know that that's the principal energy level, so I can probably come up here, and if I'm feeling really fancy, I can go, that's N. I may also even want to make a note to myself that this is the S block, this is the P block, with the exception of helium, which is part of an S, and this down here is the D block. S's start in row 1, P start in row 2, D's don't start up until down here, and they start there the third letter, so they'll start 3, so this is 4, 5, and 6. F is the fourth letter, so it starts in 4 and then 5. And now I've got my principal energy levels for all of my blocks or principal or wave formations. Now on the periodic table, there are a couple families that you need to know. A family is also known as a column or a group. Well, we call them groups or families. You in math will know them as a column. So group 1A, or family 1A, is the alkaline metals. They are the most reactive. In fact, they're so reactive that they actually explode when they come in contact with water, and therefore they must be stored under kerosene or oil. Group 2A is the alkaline earth metals. And they are also somewhat reactive. They kind of fizzle when they put in water. Actually, when they are dissolved in water, both alkaline and alkaline earth metals form basic solutions. The next major family you need to know is group 6A, the oxygen family. The more fancy term for that is the chalcogens. The chalcogens are specifically or uniquely used are in They're often found in metal ores. When we mine iron from the ground, it's typically in an oxide form or a chalcogen, and we have to remove that chalcogen from the ore. Group 7A, hopefully you remember from baby chem, is the halogens. Halogens are also extremely reactive. They are so reactive that they are not found in nature by themselves. They are always either diatomic or they're in some sort of compound. In fact, all of them are diatomic. Fluorine, chlorine, bromine, iodine are diatomic with the exception of astatine. Group 7A or group 8A are the noble gases or the inert gases. And this is because they are, for the most part, inert, with the exception of recently they were able to synthesize xenon tetrafluoride, and therefore we stopped calling them inert gases. We started calling them the noble gases. The dip in the center, the D block, is where you find your transition metals. And this is where we'll see oftentimes anomalies when we talk about periodic trends, because in the transition metals we have the least variation of representative properties, and therefore that's why they're not called representative elements. They're called the transition metals. The F block, the actinide and lanthanide series, is called the rare earth metals. Sorry, they are called the rare earth metals. And this is your modern periodic table with all the families you need to know. This is your modern periodic family. Now, the periodic table is called the periodic table because as you move from left to right and from top to bottom, there's a repeating pattern that begins to emerge. These are called periodic trends. These are observations. They are not explanations. An observation can be stated as a generalization. In general, this does this as you move from left to right and does this as you move from top to bottom. It is not an explanation. When the AP exam says discuss the periodic trend of atomic radius, it does not want you to say, oh, it decreases and increases and this is the direction it goes. It wants you to explain, compare, contrast, explain what is going on. So let's talk about what happens as you move from left to right across the periodic table. As I go from left to right across the periodic table, the atomic number increases. Let me go ahead and fill those in. Which I pray to all the saints in heaven that you remember is equal to the number of protons. All of the periodic trends that we're going to discuss can be explained by the fact that as you move from left to right across the periodic table, the number of protons increases. And since the number of protons increase, and those protons are found in the nucleus, the thing that is actually increasing is the nuclear charge, or the effective nuclear charge, which we symbolize or abbreviate ZEF. And anytime we're talking about a trend going from left to right, or right to left, we will be discussing it in terms of the effective nuclear charge. As you move from top to bottom on the periodic table, the principal energy level increases. And what does the principal energy level correspond to? If you said the principal energy level corresponds to the distance from the nucleus an electron is, you are correct, sir. And the further something is from the nucleus, the further something is from what is attracting it, the weaker the attraction. The further you are from the person you love, the greater the distance between you. The long distance relationships are doomed to fail because attractive forces dissipate with distance. And anytime we are discussing a trend from top to bottom, or bottom to top, we will be discussing it in terms of the distance from the nucleus or the principal energy level. Those are the same thing. Along those same lines, if I have a nucleus and I have more things around it, more shells, the further out it is, Any electron that wants to come and be attracted to that nucleus has to go through these shells. Those shells will shield the nucleus. So a nucleus, or an atom, an element near the top of the periodic table has less shielding than an element near the bottom. So again, anytime we discuss something going from top to bottom or bottom to top, we can also discuss it in terms of shielding. How many shells that an electron would have to penetrate through in order to be attracted to the nucleus. The final reason, the final explanation for any exception, anytime we have something that doesn't work out the way we expected it to, deals with the fact that electrons are all negative. And things with similar charges don't like to be near each other. So electron repulsion will account for the reason why we'll break the trend often. These are the only 4 reasons that you can possibly write to explain a periodic trend.